Okay. Good morning, everyone. Good morning from Brussels. We're already here with all of the speaker, not all, but one more will join later on. So yeah, welcome to the SPINMATE One Day Webinar. This is a part of the task in the SPINMATE project in work package 9, which is task 9.5. This is the part of the training pills that we will try to open and also present and explain all about the progress in SPINMATE project, especially for the pre-upscaling until upscaling, lab scale until pre-upscaling process in the SPINMATE. But this is the disclaimer. The first, all of the presentation here will be conducted in English, of course, and the second one, all of the data showed here, it's already confirmed that will be non-confidential. Of course, if there is confidential data, we're not included here. And then here the interaction is through the Q&A. So you can type anything in the Q&A about the presentation of the speakers. Today we will have 4 speakers. We will wait, I will give you the information. Yeah, this is the agenda for today. We will have 4 speakers. For the first, we will have from Serpotec, challenges and optimization of spray pyrolysis production of NMC811. And then from IREC, characterization and optimization of NMC811 cathode active materials. And then we have upscaling and solid state pouch cell assembly teams from CDTech, by CDTech, of course. And then the last speaker will be optimizing from Arkema. The title is optimizing new processes for solid polymer electrolyte upscaling. Okay, then we don't need to delay too long. But first of all, I will also try to introduce myself. My name is Rahmandika Firdausa Hari Hernanda. I am a solid state battery team leader in Avesta, but also here as the SPINMATE project coordinator, as the backup office, and also the operator and technical thing inside this one-day webinar. We also have Mafalda here, and maybe later Marco will join as well. Okay, then we can start the first session. I will give the time to Leif. Yeah, the first speaker is from Serpotec from Norway. Maybe I can briefly explain and introduce about Leif. As Leif will present about challenges and optimization of spray pyrolysis production of NMC811. Leif is a production manager in ceramic powder technology Serpotec in Norway. And yeah, you can read his background here. And I think he also mentioned here his main role in SPINMATE is produce the cathode active materials NMC811 in close cooperation with work package 3 partners, which is in a lab scale production, and especially close collaboration with IREC that will be our second speaker later. Okay, I can give the floor to you, Leif.
Thank you.
Yeah.
Yeah,
Okay.
so I'm going to be talking about first a little bit about Serpotec, the obligatory shameless self-promotion bit of the presentation, and then I'll talk about some of the challenges and optimizations we went through while we were working on the project. So yeah, after speaking briefly about Serpotec, I will do a quick explanation of spray pyrolysis before I move on to the more cathode development specific part of my speak. So just in case the internet is shut off or anything, I will start with the most important bit, conclusions, and then move on in a backwards fashion compared to how I used to write my lab reports when I was a chemistry student.
Okay.
So Serprotec started as a spin-off company from the Technical University in Trondheim back in 2007 with a spray pyrolysis furnace down in a basement. Then in 2013, we moved to our own facilities around 7 kilometers outside of the city center in Trondheim. We have an established technology through spray pyrolysis for production of a range of high quality oxide powders with unique protocols for more than 200 different compositions. We have a production capacity of between 1 and 4 tons per year, depending on the material. And we would need up to a year to scale this up to a more industrial level. We have a fairly large customer base and are in ongoing qualification processes for becoming a regular supplier. Most of our customers are the R&D departments of various industries. Next slide, please. Yeah, so we can produce large volume, anything from say a kilo to 100 kilos is doable at the moment. We are partners we like to be partners in development projects and collaborate in piloting with the intention of future scale-up. We are also quite happy to be partners in, for example, EU projects. So we're currently involved in, among others, SPINMATE and Advergen in the Horizon Europe setup. Next, please. Yeah, so spray pyrolysis, which is our production method for mixed oxides, consists of a pyrolysis step, which is a continuous process, then calcination, which we currently do in crucibles in chamber furnaces, and milling and sieving, and usually also a second thermal treatment to remove any residual mill jar or other organics that might have entered the powder during processing. We produce agglomerates with well, of submicron powders. The crystallite sizes vary from 10 to 500 nanometers, depending on calcination temperatures and what type of material it is. We achieve surface areas usually in the 1 to 50 square meters per gram area. Yeah, next slide, please. So in more detail, spray pyrolysis consists of producing first a solution mix of the cations that are going into the mixed oxide. We spray that through a nozzle into a rotary furnace at between 800 and 1100 degrees Celsius. Then we get a shell of metal salts that starts to decompose into oxides already in the spray pyrolysis, and we finish that conversion from precursor salts into oxides through the calcination step. Then we end up with a powder that consists of hollow, more or less spherical particles, and we break those down into a finer powder through a milling step. Yeah, we also have in-house XRD, and we use the local universities PSD, SEM, and BET services, and SINTEF or other labs can do ICP for us as well if desired. Next slide, please. Yeah, so the main advantages of spray pyrolysis is high stoichiometric control. We usually achieve high purity and phase purity, since we don't have the same issues with having the raw materials, leftovers of the raw materials in the finished product. So we get some of the advantages of the sol-gel lab synthesis route, only on a larger scale. The green elements here are elements we have worked with so far. We're not too keen to move into the radioactive ones, of course, and we try to avoid stuff that either will harm our furnaces or is highly poisonous. So we won't do lead, for example, or cadmium, or quicksilver, or mercury. And it's very hard also to use and work with the noble elements like gold and platinum, since we can't dissolve them. So we get some, our powders get some of the advantages of nanoparticles, but the powders are usually loosely agglomerated, so that it is easier to handle than an actual nanomaterial, but the sinterability is closer to nanomaterials than they are to solid state reaction powders. It's also a fairly scalable production method. Yeah, next. So now we move on to the NMC, and my conclusions so far of the work. We look at our competitive advantages in oxide powders in general, and see if they are applicable for NMC production as well. So the stoichiometric control, well, we had some issues there, but we managed to fix them in the end. Going to be talking more about that later. Phase purity was okay. Yeah, but we had these stoichiometric issues with initially losing both nickel and lithium. And there are issues with lithium carbonate formation on the surfaces, since moisture control is a big challenge for our production in our production facilities at the moment. Small particle size, well, that's not necessarily a huge advantage for battery cathode use. So if we're going to have commercial success with NMC through our production method, we need to find narrow applications where smaller particles is an advantage and not a problem. The narrow particle size we have, it's partly countered by sintering tendency during our calcination step for NMC. There's a minor liquid phase that forms that we'll see in some pictures later. Sinterability, very few people or companies aim to sinter their batteries, so that's not very applicable. We would need better moisture control and more continuous calcination furnace. Scalability, the spraying is scalable. Calcination is probably scalable through switching to a rotary furnace for calcination as well. And the main keys to improve are control of moisture and CO2. And the picture under the periodic table here is a sample picture that is included in all our presentations at the moment. And I think this is an oxygen conducting material. So just move on to the next slide, where we're going to talk about results and discussions. So I've mentioned stoichiometric control challenges. We started by mixing stoichiometric amounts of all the cations, including lithium, sprayed it into the pyrolysis, and for the first batches, we had very poor yield, as low as the worst was at 30%, and we slowly increased it. And the main reason was that we produce fines that bypass the powder collection setup and end up in emission filters. And these are two pictures from the emission filter. There's lawn mowing going on just outside my window at the moment. I hope you can still hear me okay. Yeah, so the first picture is from a production where we finished on a Friday, and when we came back on a Monday, tiny needles had started to crystallize on all the surfaces in the production facility. So both inside the furnace tube and on the filters. So that gets clogged, and we struggle with pulling air through the furnace. We later found, or IREC discovered, that we were missing some nickel. So we checked the content of are filters the powder that is not collected, and we found that that was quite nickel enriched. You can see there's some barium and zirconia there as well. That's old fun from a previous production of proton conducting material. So there's a tiny amount of that still left in the filter. So we've done EDS analysis at NTNU. It's not extremely reliable when you do it on a small sample of powder. I've stripped away the aluminium here, for example, due to the sample holder. But we see that there is more nickel here than there should have been. And that's the stuff that's missing from the cathode material that we actually collected. Yeah, I think we can move on. So we also found that the poorer our yield during spraying, the worse the stoichiometry was. So when we managed to improve yield up to or towards 90%, and by using organic additives, we believe that we both produced a finer powder that and a more uniform powder, so that the material we lost was no longer as nickel enriched. And we also lost a lower portion of powder, and both those help with the nickel loss. We also found that we have lithium loss. This was a lot less surprising, and we coped with that by doing a small-scale test with different amounts of excess lithium, and we landed on 10% lithium excess for the upscaling process. Move on to the next one. Calcination. This is probably where most of the lithium disappears. And in the beginning, I used bigger crucibles because we were having in mind that we wanted to make maybe as much as 20 to 40 kilos of the material, and bigger crucibles would be better. The challenge was that in order to get good structure of the material, we needed to go so high in temperature that we ended up with a lump that you can see on top of a sieve towards the right, at the right-hand side here. So when you want to make a cathode layer, a particle size of 10 by 10 by 5 centimeters is a bit on the coarse side. So we also found that we got better cation mixing and uniformity of powder with smaller samples. So we decided to get hold of lower crucibles and rather stack them in 2 or 4 layers. So we ended up with staying between 10 and 12 millimeters of spray pyrolyzed or raw powder, as we call it. And I also discovered that if I divided the powder into smaller heaps, they would stay separated. So I had smaller lumps to crush during the milling process, which you can see here. After calcination, I removed the crucibles from the furnace at between 200 and 150 degrees and placed them under an argon blanket to minimize the effect of moisture and CO2 from the air. We used 12, 16, and 20 hours of calcination at 850 degrees. And we had the best results with 20 hours. I think we can move on to the next step in the process. So after calcination, we did dry milling. Most of you will probably have a smaller version of these mills in the lab. It's a simple roller mill. We used 20 millimeter yttria stabilized zirconia beads for the initial 24 hours. Then we separate this in a very coarse sieve and then move on to a stack of 250 micron sieves. The reason why we used two was that we had some larger particles that seemed to have bypassed the one sieve at one moment. So to be less likely to break the ductile blades of our colleagues, we added a second sieve. After the first 24 hours, between 25 and 50% of the milled powder passed the sieve, usually closer to 25 than 50, unfortunately. So this we remilled with smaller beads. And we also filled the mill jars with argon gas to at least reduce contact with moisture. And we also used argon flow during sieving, where you can see there's a tube going into the orange lid on top of the sieve there, and you can also see that the collection bag is inflated. After well, all the powder that passed the sieve, whether it was after 24 hours of milling or 48, we I think maybe move to the next slide for this actually. Yeah, IREC found that there was a varying amount, but a significant amount of carbonate on the surface, not enough to show up on our XRD, but they could detect it by methods that are more sensitive to surface conditions. So we tested annealing the powder for 12 hours at 700 degrees following the sieving, and you can see the top green line here. The CO2 peaks are at 1400 and 900, I believe. Mark will probably interrupt me if I'm misremembering, but yeah, the top green line here, you can see that that has been more or less completely removed, and this also gave better electrochemical performance for the powder. So we introduced that as our second to final step. So we produced by spray pyrolysis, followed by calcination, milling, sieving, remilling to improve yield, sieving again, and a annealing process. I skipped calcination. Right? Calcination 850 and annealing at 700. Then we packaged in aluminium pouches, which we filled with argon alongside the powder. Let's see. Did I have much more? Acknowledgements. I see my colleague's picture has fallen out. No, there they are. These are my colleagues at NTNU. The three handsome people towards the right there are our founders, Professors Marianne, Kjell, and Tor. And the rest of us are the two number 4 and 5 from the left are members of our board, and the other 4 of us, we work in production and anything that's hands-on. On the left here is our CEO. I think I got all our partners in the slide as well. We couldn't have done this without our partners, and especially IREC has been very central to producing a cathode with at least decent electrochemical properties in the end. I will hear more maybe about how it works in scaled up production later.
Yeah. Thank you, Leif. So yeah, here's the challenge and also the approach that we have done for the NMC 811 synthesis, and it's handled by Serpotec together with IREC, of course. And yeah, afterwards we'll see how we characterize the NMC 811 from Serpotec to be upscaled in SPINMATE project by IREC. Okay, thank you, Leif. Then we'll leave the Q&A session by the end later. So we'll continue with the presentation from IREC. Then, yeah, this is the SPINMATE project. Yeah, this is the last slide from Serpotec. Okay. Then, yeah, we can move on to Mark. Here, I briefly introduce Mark first. Today, he will try to explain and enlighten us about the characterization and optimization of NMC 811 cathode active materials, mostly what we've done in SPINMATE. And yeah, Mark is a postdoctoral researcher in the IREC, Fundació Institut en Energia de Catalunya. So if I'm not mistaken for the spelling. And then yeah, in SPINMATE, Mark is closely working together with Leif. Here, yeah, like Serpotec is making the NMC 811, then IREC will help with the characterize, then analyze. Okay, this is, we can go or no go with the decision. So yeah, here it is. I will give the time to Mark.
Okay, thank you, Ramandika, for the introduction. So I believe this is a presentation that maybe would have been helpful to be first than Leif, because now I will be talking about what do you seek when you are looking for a good NMC 811 material, more in the lab scale than in the A-scale up. So what is a good starting point and which are the more valuable techniques for its characterization? And link that characterization, these physicochemical properties with a good electrochemistry. So if you can go to the first slide. Okay, NMC is an interesting material. It has a layered structure. This layered structure is formed by a layer of lithium atoms and a layer of transition metal atoms in an hexagonal pattern, and these are coordinated in a octahedral electrochemical configuration. In this case, the NMC 811 material has in its transition metal layer 8 atoms of nickel for each 1 atom of manganese and cobalt, but there are other NMC materials. However, NMC 811 is interesting due to its high specific energy, which theoretically it should be around 275. However, experimentally, you should be around 180, 200 milliamperes hours per gram. Compared to other active materials such as LFP or other ones, it shows a poorer cycling stability. So in the end, when you're doing some batteries with NMC, it's because you're looking for an increased specific energies, a larger energy density. So looking for, in this case, for a wider range for EV vehicles, for instance. However, one of its drawbacks is that it's a very challenging material to synthesize. And that's why this presentation focuses on how to do this synthesis. And can you go to next slide? Okay, there are several parameters that affect the performance of the NMC 811. And the first one is the lithium nickel cation mixing. This is an effect that occurs when the lithium and the nickel exchange positions in the crystal structure. This happens when the nickel is in a 2+ oxidation state, showing a similar ionic radius as the lithium. So in this case, when you switch these positions, what are you causing is hindering the lithium diffusion and also reducing the capacity of the material. So you are always looking for diminishing this effect. And one of the ways to diminish this effect is by making sure your nickel 2+ is in the minimum quantity possible. Another effect affecting the properties of these NMC materials are the surface impurities. The surface impurities usually formed by lithium and nickel, which are the most reactive elements in the surface of this NMC 811, because they are also the most abundant ones. And they react with carbon dioxide from the atmosphere or even water vapor to form carbonates or hydroxides. The same goes for these kind of impurities. You are reducing the amount of lithium and nickel active in your material, so you are reducing the capacity, and at the same time they act as resistive elements. So in the end, you want to be removing all these surface impurities and also increasing the lithium nickel cation mixing. And how do you evaluate what is this lithium nickel cation mixing? So can you go to next slide, please? So one of the most powerful techniques to be able to do that is X-ray diffraction, where just by simply looking to the patterns, you can take a lot of information. Can you go to, just can you move next slide? So from just this pattern that it's one from a commercial sample and another is one of the samples that we synthesized during the project, we can have an idea of the crystallinity of the sample by looking if the peaks are broad, you see, and they are not well separated, they are merged together compared to the commercial sample. You know that your sample has low crystallinity. You can also estimate the cation mixing by the intensity of the higher intense peaks of the NMC, that are the ones located in the Miller index position of 0.03 and 1.04. If you divide those intensities, you should be getting around 1.2 or higher value. If you are below this value, you are known that there's a significant cation mixing that should be 10% or higher in those samples. And last, even if it's not the best techniques, you can also, if there's a huge amount of carbonates, you can see them in their in this position between 20 and 42 theta position. That is where there's the signals with high intensity. However, this is just for looking the patterns. But if you go even deeper on this technique, can you just go to the next slide? You can refine this data by some open software as is GSS2, that the one that we use it. We use it for doing this Rietveld refinement, and you can have a look at further information. And this is to get the cell parameters, that it's these A and C, that should be in this this range between 2.86 and 2.87 for the A lattice parameter, and for the C parameter between 14.18 and 14.25. So that's one thing that we can measure with this refinement. There's also the crystallite size that correlates with the crystallinity of the sample, and also you can refine to have a very more quantitative value of this lithium nickel cation mixing. So this would be for the XRD technique. We can estimate this lithium nickel cation mixing that we're mentioning. For next one technique that I want to mention is the Fourier transform infrared spectroscopy, which is a very sensitive technique to surface impurities, in this case for carbonates impurities, having these broad absorbances, the carbonates bonds in these regions of 850, 1000 and 1400 wave number lengths. So this is a powerful technique to be able to identify if there are carbonates on your sample in your surface sample. And last technique I want to mention to characterize these materials is ICP. ICP is a very powerful technique in order to measure the quantity of the concentration of your elements. Usually, most of studies only study the lithium concentration because it's an element that when you calcine at high temperature, you're expecting it to evaporate. So there would be always some kind of, or is expect some kind of lithium deficiency, but it's also very important to check the other elements. And ICP, that it's induced coupled plasma technique, can be coupled with an optical spectroscopy technique or with a mass spectroscopy if you want to go for maybe lower concentration rates, it can help you with identifying the right composition on these elements. So all that needs to be combined with also with another characterization technique, but it's electrochemical techniques. Ramantika, can you go to the next slide, please? Okay, so we did different electrochemical. There are a wide range of techniques that you can use to characterize, but in this presentation, I only will be showing some results from some cycling tests. This this protocol consisted of a voltage range between 3 to 4.3 volts, 2 formation cycles at C/20, and then 100 cycles at C/10, and assuming a capacity of 200 milliamperes per hour per gram, which is the value expected for a good NMC material for a commercial sample. And all these tests were done in a coin cell with liquid electrolyte using a LiPF6 and DAC-AC and Celgar membrane separators. So before starting with the optimization, this is the typical result that you get from this kind of electrochemical characterization. You get the specific capacity that in this case would be the discharge capacity of the material. And also you can evaluate the capacity retention. It's usually how many cycles till you get 80% of your initial capacity. So this is normally what is evaluated from this type of test, and that's the one that will be showing in order to evaluate the performance of our material. Although, as I mentioned, there are other techniques that can also give any other types of information, but due to time constraints, I will stick to that. So can you move to the next slide? So in this case, this powder, as Liv has been mentioning, has been done via spray pyrolysis. I won't be spending too much time on that. But in the end, you are obtaining a raw powder from a nitrate solution, a stoichiometric nitrate solution, and then you need to calcine this raw powder because it's still there's not formed the right crystallographic structure. There's still a mixture of oxides, carbonates, so you need to do this calcination, and then you also do some processing for the electrode preparation. However, if you look at this schematic representation of the process, we need to find or look in which points we can act in order to optimize this material. And to do so, if you move to the next slide, we identified three points. One, the thermal process, the calcination and the time, and the calcination temperature, the gas atmosphere during the calcination, and also the precursor solution. So I will be explaining each one because this is the way that we went for this optimization. So the first one was the thermal process, and we started with, can you move to the next slide, please? We started with 4 different temperatures that were 700 degrees, 800 degrees, 850, and 900 degrees for 6 hours. So these are the electrochemical results, and what we observed was that 700 and 800 degrees didn't give any good capacity, and until we get into higher temperatures, that was 850 to 900, we start to get some better results. In the case of 850, this is the one that gave a higher discharge capacity. This was about a value close to 140 and with a capacity retention of 11 cycles. However, this is not a really good performance, so we needed to check what was happening, and to do that, let's dive in the physicochemical analysis. And we'll start with XRD. In this case, I'm showing them the spectra of these samples, and we can see that these 700 degrees and 800 degree samples show a really poor crystallinity with broad peaks, with not well-defined splitted peaks, while when you increase the temperature, you obtain a much higher defined peaks with better splitting. And if you also look at the lattice parameters that I was mentioning at the start, you also see that these 700 and 800 are not in the right range. Looking at the nickel antiside effect, this lithium-nickel cation mixing, you see that by increasing the temperature, you also get a lower nickel cation mixing. However, what is still in a very high value. To look, I'll just in this case a bit the morphology and also correlate that with the crystallinity of the samples. Can you go to the next slide? Here's is the same imaging of these samples. We can see that 700 and 800 degrees, you can see the secondary particle of the materials, which is this round or spherical shaped particles that are hollow inside, but you can, at these magnifications, you cannot see the primary particles. In the case for the 850 and 900, you can see the primary particles that are much larger. And this one, doing the refinement that I was mentioning, you can obtain this crystallite size, and you can see that for these lower temperature ones, the crystallite size were around 30 nanometers, and by increasing the temperature, you increase this crystallite size up to 150 to 100 nanometers. So when seeing these results, we saw that this cation mixing was too high. That was explaining the bad performance, but we wanted to also check for the carbonate impurities that we were mentioning. So for that, we did some IR spectroscopy. Can you go to the next slide? For the Fourier transform IR, we observed that for all the samples, there was this absorbance peaks that were I have marked in the figure that indicate there's a high quantity of carbonate. There's a significant presence of this on the samples, and that correlates with the fact that we are synthesizing them in an air atmosphere. So it's very likely to happen this kind of reaction between lithium, nickel with this atmosphere carbonates. So for the next step, the idea was to remove all these surface impurities and also try to improve the nickel cation mixing. And to do so, we assess the calcination atmosphere of the sample. So if you go to the next slide, for that, we consider 2 atmospheres. One is synthetic air, that it's the same as air, but we are removing the CO2 of this atmosphere. And the other was oxygen, with also doesn't has any carbon dioxide, but we also go for a more oxidative atmosphere, that the idea is to reduce the amount of nickel 2+ on the samples, to go for a fully oxidized material and try to reduce the number of nickel 2+ ions that are the ones that swap with the lithium. So when we did the electrochemical assessment of these materials, we saw that both of these materials showed better electrochemistry. The synthetic air showed a discharge capacity of 150 with 15 cycles of capacity retention. And the oxygen material even got a better performance with 160 milliampere hours per gram with 24 cycles. So now we wanted to check what happened to the samples, and to do so we again looked for the XRD of these samples. Can you move? Okay, thank you. And now we see that the synthetic air material shows a lower cation mixing, And even if we go to the oxygen one, we saw an even lower cation mixing that is around 8.5. So it seems that by eliminating these surface impurities and increasing the oxygen in the atmosphere, we achieve this reducing the the cation mixing. However, we're still far from this 180 to 100 milliampere hours per gram that we're expecting for a commercial sample. We also wanted to make sure that the carbonates have been removed. So for that, we did some IR again. Can you move to the next slide? In this case, if we compare the first sample, that is the blue one, the dotted blue one, with the other ones that are the synthetic air in red, and the black one is the oxygen. Once we see that the amount of carbonates have been significantly reduced, it's almost, we cannot see any signal coming from the absorbent of these carbonate bonds. So in the end, we assumed we have achieved to reduce or to almost eliminate all carbonates, so there's no impurities on those samples. However, as I mentioned, we are far from this good electrochemical performance what we're expecting for this kind of NMC811, and to do so, we assessed the composition or the stoichiometry of the samples. Can you move? Next slide. And to do so, we did some ICP measurements. And what we did see was a bit surprising, not so much for the part of the lithium that we were expecting some lithium evaporation. In this case, if you check the lithium of the samples, you see that there's a 10% deficiency on all the samples. It should be around 1, not 0.9. But there's also a higher amount of cobalt and manganese when compared to the nickel element. So in the end, we needed to assess, in one case, the lithium excess. We needed to increase the quantity of lithium to compensate for this lithium loss. And at the same time, we needed to correct this stoichiometric ratio to be in the right proportions. Because what we thought was, if manganese and cobalt show a higher oxidation state than nickel, it is possible that, since to compensate the electric charge of the material, you would need to compensate that by reducing the oxidation state of nickel. So increasing again the concentration of nickel 2+, so increasing the lithium nickel cation mixing. So in the end, if we assess this composition and we stick to the right ratio, we should have the minimum amount of lithium nickel cation mixing, and so a better performing material. So if you move to the next slide, the last thing that we checked was these two different samples. One that show we added 10% excess lithium in the precursor solution that we call lithium, and also a second sample with this 10% excess lithium, but also we corrected this stoichiometry to be on the 8:1:1 ratio. And the electrochemical performance for these materials was much better. In the case for the excess lithium material, we see discharge capacity around 180 and 25 cycles of capacity retention. And for the good stoichiometry, we got close to the 200 milliamperes per hour per gram and 32 cycles. So now we are on the right performance of this kind of materials. And we compare these materials with some commercial sample that we bought from MTI. Can you move to the next slide? That it's a sample obtained from co-precipitation. We see that this initial capacity for both of these materials are on the same order. So we have obtained a material in the same with the same similar electrochemical performance as the commercial material. So now we wanted to finally check all these physicochemical parameters. So first we started with the ICP, and we saw that for the excess lithium sample, now we are seeing that the lithium is in the right concentration. It's close to this 1 value, but even if we add the lithium, we still saw this inhomogeneity on the cobalt and manganese composition. But in the good stoichiometry sample, we saw that now all the elements are in the right composition, showing discrepancies below 5% for all these elements. So in the end, we are having a material that has the right stoichiometric ratio. And if we compare this with the ICP obtained for the commercial sample, move to the next slide. We saw that in this case, the commercial sample also show similar discrepancies below 5% when compared to all of its elements. Lastly, if we check also the XRD information of these samples, we see that the the excess lithium material shows an improved cation mixing value around 6%. That's pretty good. However, if we go for the good stoichiometry, now the cation mixing is very low. It's around 2%, which is in the order of commercial samples. Because we also did some XRD on the commercial sample, and we observed that this nickel anti-side effect is in this order of 2-3%, that it's what is expected on a good performing NMC811 material. And we also, if you look at the lattice parameters, both of the good stoichiometry and the commercial sample show almost identical lattice parameters that are in the range of the NMC811 material. So to summarize and end this presentation, let's do just a summary of what we observed. And so in order to obtain a good performing NMC811 material, you need to have a material with a high crystallinity, low cation mixing, no carbonate, and with the correct stoichiometry. So which are the most interesting techniques or more valuable techniques to be able to assess that? And that would be XRD for the crystallinity and for the cation mixing, Fourier transform IR for the carbonate impurities, and lastly ICP for the stoichiometry. And so if you have identified these problems, how do you act? How do you improve those? So for the crystallinity, the best way to do that is for the thermal treatment. Remember from the first slide that I showed this SM imaging and the crystallite size. So in order to improve this crystallite size, what we did was increase the temperature, and the crystallite size increased considerably. Then the carbonates, the best way to remove that is to tackle the gas atmosphere, to go for a gas atmosphere without carbonates, without carbon dioxide. And also, if you can go for oxygen, it's even better, as you saw from the lithium nickel cation mixing. And lastly, the stoichiometry should be assessed for the precursor solution. And in the end, if you assess all these parameters, crystallinity, carbonate, and stoichiometry, you will end up with a good lithium nickel cation mixing, which is what it's making the material to work finely, to work as expected for an NMC811 material. So to end this presentation, I would like to thank the funding received from the European Union's Horizon 2020 Research and Innovation Program for this SPINMATE project, where I've been able to do all these characterization and synthesis activities. And also I would like to thank Serpotec, which is the partner that I've been working a lot for trying to optimize this NMC11 in this lab scale synthesis, and also all the audience for its kind attention. So thank you.
Yeah, thank you, Mark. It's an interesting presentation, actually. So we can get the key performance and also the characterization steps that we need for NMC811 production or synthesis. Okay, then we can move on to CDTech. Then thank you, Mark. Again, we'll try to put everything, the question and the discussion by the end of the all of the presentation. So I will move to our next speaker. Yeah, our next speaker is from CDTech. We'll talk about upscaling and solid-state pouch cell assembly tips from CDTech, of course. She's Marta Cazorla Salt, researcher in CDTech Energy Storage. And yeah, in the SPINMATE project, she worked with closely with everyone, actually, like every partner to produce the solid-state pouch cell assembly and also lab scale trials for the electrochemical testing. So yeah, I will give the time to Marta.
Thank you, Ramandika.
Yeah.
Do you hear me correctly? Yes.
Yeah.
All right. Thank you very much for the kind introduction. So in my talk, I would introduce the upscaling and solid-state pouch cell assembly that we do in CDTech, which is a crucial part in the SPINMATE project. Within all these activities are part of. I'm part of the solid-state battery team of the Materials for Energy unit in CDTech. So if you can go to the next slide. So I will briefly introduce CDTech first, and then I will explain the context and introduction of why it is important to scale up, and then electrode processing, cell assembly, and some take-home messages. So first of all, about CDTech. So we are an organization for applied research. We have three main institutes. One, it's about surface engineering, nanomedicine, and energy storage, which we're part of. We're located in the north of Spain, in San Sebastian, and we have new facilities from 2025 with a big amount of dry rooms and a very extended pilot line. So we are positioned in in a lot of steps in the batteries value chain, from the research and development of battery materials, but also cell manufacturing, battery packs, applications, and end of life. So the sectors or the customers that we work with, they are part of the battery materials industry and manufacturers, but also electromobility, energy companies, and other niche markets. And about the solid-state batteries in the next slide. So these are a bit like a small overview of the equipment we have, from slurry and dry mixing, electrode coating, calendering, cutting, stacking, and cell assembly, and electrolyte filling and degassing, all in both manual and automatic way. We will see it in a bit how we have used some of these equipment into the SPINMATE project. And so in CDTech, our activities within solid-state batteries, we mostly work with, we both work with lithium ion, lithium metal, and anode free. And we focus on mostly polymer-based solid and semi-solid electrolytes. So we do the processing, upscaling, and we work with gel polymer electrolytes, hybrid gel polymer electrolytes, and also a diverse list of anodes, lithium metal, also mixed graphite silica, etc. And as well as a wide range of cathode materials. So this is a bit the introduction of CDTech. And if we go to the next slide, we can go to the scale-up project. So the scale-up, first of all, so as our colleagues from Cepotec and IREC very well explained, in the research of SPINMATE, we are developing solid-state batteries. So with respect to the standard liquid electrolyte batteries, in which we have porous electrodes, you can advance the animation. Sorry, Monica, I'm going a bit too fast for you. So in which we have some porous electrodes with active material binder and other conductive additives. All is wet by a liquid electrolyte, which gives a good wettability, but it has flammability and volatility. So with the solid-state batteries, as the ones we work with SPINMATE, we have also a porous electrode, but it's, as you may already know, it has a cathode component. That's if yes, thanks. So our cathode acts as a solid electrolyte, which allows the ionic transport of lithium ions from our active material to our lithium metal negative electrode. And we use solid electrolytes, which allows to remove this liquid injection during the assembly process, but also we improve the safety. But we also need to assure that the contact is ensured at the different interfaces of our system. So if we can go to the next slide. So as I said, the material development is important. In SPINMATE, it's done thanks to other partners. But then we need to upscale to be able to see the application at different states of research. So typically we start with coin cells, but these have a limited capacity and no pressure control, even though they allow to have a quick and cheap validation of some materials we want to screen. But at the end, the objective is to go to pouch cells, which is the next animation, and with which we can have higher capacity, and then we can work with a design that is closer to the final cell design, and we can have a better control on the external parameters, the development and validation of these components that we have processed and developed in earlier stages. And also we can assess safety, KPIs, and cost engineering. And as I said, like going to higher capacities, so 5 ampere hours or 20 ampere hours in the case of what we do in Unity. How this goes? So from our initial configuration, we do a lab scale development. This is around 50 or 500 grams maximum of slurry. So this slurry we process, we optimize it, and then we characterize it. So it's very important to control the viscosity and the homogeneity of this slurry for a proper coating. Then we do it at small scale with using Dr. Blade equipment. And we calendar these coated electrodes, and then we see how its morphology, addition, the electrical properties, and then we do electrochemical testing at a small scale. Once this is done, this requires several iterations, and then once the formulation is optimized, then we can go to a pilot plant upscaling, in which we prepare higher amounts of slurry, and then for that we need a higher equipment, and this is the pilot lined equipment that we will see in a minute. What are all these steps? And they allow us to reach the final format pouch cell assembly that we need, and to again validate it, because then we also need to go back to iterate back in the process till reaching the final configuration. So this is a bit how it's done. Then how it's actually done properly. What we've done in SPINMATE to upscale these electrodes, positive electrodes that we've been working with. So the upscaling has different steps. So first is the mixing of components. Then we have the coating and drying of the electrodes. Then it comes the calendering. It's a very important step. And then the electrode notching or cutting into a certain shape of certain dimensions before assembling finally the cell with the final results. So now if we go a bit into each step, you can, yes, thanks. So mixing the electrode components, if we're preparing such big slurries, then we need powerful and appropriate mixers. So we have different type of mixers depending on the volume of slurry and the formulation we're working with. We use one of the other. This is an example of the mixer that was used in SPINMATE. And another parameter that is very important when we're doing the mixing is the next point, please. It's how we mix these components, the order. So in a cathode, in a positive electrode, we first start preparing the catholyte solution. And then we add the conductive additives and the active material. There's some resting time between components, and all this mixing is done at a certain speed. And for the quality control, then it's very important to measure the temperature and the power control during the mixing. And also, once we have the slurry, the mix itself, we do some rheology. We monitor the flow curve and thixotropy test to see how, I mean, it's important for the slurry to be viscous, because then we don't want all the components to precipitate, and because this will cause some heterogeneities in our slurry. So we then see the presence of aggregates. This is called granulometry. It's basically to put a certain amount of this slurry on a grindometer, in which we can see the size, we can measure the size of the aggregates, possible aggregates that are present in the slurry. And during all this process, we monitor very well the solid-liquid ratio, because we need a certain amount of this ratio to allow the coating process to be smooth. So in the next step comes the coating. So here it's very important to define properly which loading level. So it means how much active material we want on our layers, and also its density. This will be controlled afterwards with the calendaring, but already we need to have it clear. So in Sidetec, we do it in this type of Coatema-based coaters. So we deposit the slurry, and then we have the coated electrode, that this is then dried at a certain temperature and speed, and then again all the time we measure the thickness and the loading control, having some tolerance windows. And this step, it's also important to see, because we can have many issues at this step. So it is important to control what's the gap, that it's the space between the coater, in which that will actually define how thick and how fast our coating is being deposited. But also the coating speed, the drying temperature, and because we can have problems such as pinholes, fish eyes, as we call it, or air entrainment, that is causing bubbles, and then streaks, that it's because of we have maybe some aggregates that then get pulled all around the deposition, or agglomerate, because we could also be having some heterogeneities in our slurry. So these are typical problems that we encounter, and that we need to iterate on top till reaching the accurate coating as the ones we've managed to have within SPINMATE. So then while we have the coating, there's a very important step, that is the calendaring. So the calendaring, first of all, like when we have a coated electrode, here we see in this magnified picture, we have lithium ions that transport through the cathode. So in our active material particles, we know that these are lithium ion conductive. But then when we reach some pores, these pores are not lithium ion conductive, because this is the solid electrolyte, or catholyte as we call it as well, allows the lithium ion transport. So we want to reduce this porosity to assure that we have a correct lithium ion transport within the electrode matrix. So for that, we do some calendaring. That is basically a way of increasing the density of the electrodes till our scope value in a controlled way. So for that, we also improve the addition to the current collector and the final electrode thickness. And then there's a picture of the equipment, the Nacknor roll calendar that we use in Sidetec, that we use also for the SPINMATE electrodes. So calendaring, it is important, but it also has a limit. So this is a semi-image before calendaring. And then when we calendar, we have like a smashed distribution of our electrode, in which we have reduced the porosity. and we have a more dense electrode that is something that we want, because we want dense batteries with dense electrodes. But then if we calender too much, we can have cracked particles and also some mechanical tensions in the current collector that can lead to the final rupture. So it's very important to find a limit that gives us a correct performance. So next, the next step is the notching or the cutting. So because when we get the coated electrode from our equipment, we have it in a roll. So then we need to cut it into sheets, different parts, and then we notch it with a certain geometry. Here it's very important to leave, as you see, a non-coated part that is actually the tabs in which the electrical connection between the cells, between the electrodes, sorry, for a certain cell will be done. So here is an example of an anode, a solid electrolyte and a cathode that we have cut and then assembled in a SPINMATE cell. This is done manually, but it can also be automatized once the technology is at a more advanced step of the design. So once we have the electrodes, then we can go for the next step, which is the assembly. So here it's a bit of a summary on how this is done in SPINMATE. So as I've told you, I've explained you what we do in CBTech. So we take active and inactive materials, we do the mixing, coating, calendering, notching, and final drying. These active materials come from Serpotec that, as you've already watched, it was developed with the help of IREC. And once we have our cathodes and our anodes that are done by Avesta, we notch them, so we cut them into a certain shape, depending on the capacity of the cells we're assembling. And we also have the solid electrolytes. Here, this is upscaled by Arkema with the support of SiC Energy Gune. And once we have all the components of our cells, we do the cell stacking and tabs welding, packaging and sealing, again, some quality control that we will see in a minute. And we do a formation cycle. A formation cycle is like a preliminary electrochemical formation that allows us to have a controlled formation and first discharge of these cells before having the following electrochemical testing and delivery to the rest of the partners of SPINMATE to do their characterizations. The assembly. Once we have the cell components, we assemble these using certain guides, because as I commented, that this is done in SPINMATE manually. We have the tabs, we weld them together, and there's packaging and sealing step till reaching the final cell as you see it in these pictures. So at this point, once we have this cell, there's certain parameters, control parameters that we called, that we measure to be sure that what we've produced is into the line of what we expected. So these parameters are cell weight, the thickness, also the volumetric and gravimetric energy density, the internal resistance, the open circuit voltage at different states of charges, and the first discharge capacity that we obtain in this formation cycle that we just commented. So these parameters are also used in SPINMATE for all the machine learning based activities, because this is a very useful database to then monitorize how these cells are performing at the different characterization tests that are done within the project. So once we have the pouch cells, then there's in CBTech, we've also done electrochemical testing and validation. So here we see a cell, it's in its final configuration using a jig in which we are applying a certain pressure. And during this, with this certain pressure, we can then share different cyclability testing at different temperatures that we perform in SPINMATE, but also we can investigate and monitor the different voltage profiles, charge profiles, internal resistance analysis, and so on, as well as Coulombic efficiency and capacity retention. So this is what we do in SPINMATE from CDTEC. And if we can go to the next slide, I wanted to include here some important messages from what we've seen today. So it's very important to have a high quality cell to have high quality components. This is obvious, but it's not always the case, and we have the chance in SPINMATE to have very high quality components that we can assemble in a cell and have in our different characterizations. Then at each step of the assembly, you've seen it has a lot of process, a lot of steps, and it's very important to have quality checks to see where we have any possible deviation during the assembly and electrode processing. And so at each step, we will see that it's always happens that we have a certain iteration. So we go back in development in different formats. That's why it's crucial to gradually increase the format of the cells from low capacity to high capacity to different formats, from coin cell to pouch cell. From the slurry preparation and coating are very critical steps. Then the calendaring, as you've seen, it allows to decrease the porosity and have high density electrodes, but it always has a limit. And the humidity is the silent enemy. So here it's very important. We do, as I commented, we do all the assembly in dry rooms. So the humidity is very well controlled. And we assure that we don't have degradation of components during the assembly. So upscaling is crucial because sometimes the results that we can observe and study in a coin format don't always align with what we see in the pouch format. So as I said, yes, upscaling is very important. So that's it for now. I would first, before finishing, I would like to acknowledge my team in CDTEC. This is the solid state battery team, but also the pilot plant team and the electric lab team. And as well, the SPINMATE consortium, all our partners that we work closely at different aspects, and here are all summarized. And of course, the funding of the European Union that is making possible all this joint work. So that's it from our side. Thank you very much.
Thank you, Marta. That's an insightful presentation as well. So here, after we synthesize the materials, then we do the characterization, then how we make the cell. And then beside that, you also see the process that in between we will have the battery component, lithium metal, and then we have a cathode, and then we have the polymer electrolyte. So afterwards, we'll try to explain about how we make the solid polymer electrolyte, and it will be delivered by Hiram. Okay, thank you, Marta. Then we move on to the next speaker.
Thank you.
Yeah. So yeah, our next speaker will be from Arkema. Hiram is the R&D engineer, battery materials from Arkema. He will deliver about the optimizing new processes for solid polymer electrolyte upscaling. So in this in the SPINMATE project, Arkema helped to get the most of the Arkema materials in the solid state electrolyte, especially for the polymer. So I will give the time to Hiram.
Thank you, Ramandika, and good morning to everybody. So first, thank you for giving me the opportunity to discuss a bit about the work we are doing in SPINMATE. And like Armandika said, I will talk about the optimization of the processes for the solid polymer electrolyte upscaling. So if you can move to next slide. I will first give you some information about Arkema. I will try to be short, and then I will so focus on the main topic, which is solid electrolyte manufacturing. So I will first recap the lab scale process that has been developed in SPINMATE, and then talk about the challenges that were faced during the upscaling, and then we'll finish with some takeaways. Yeah, so yeah, thank you. So Arkema is a leading company in innovative materials for a sustainable world. Really, our vision is to offer the most innovative and sustainable solution to address our customers' current and future challenges. And customers are the key in all our developments. You can go to next slide. So we have different kind of activities in many fields, but we can summarize them in three main topics. First one is the creation of the triangles of materials. The second one is the bonding and assembling of materials, so everything concerning adhesives. And the last one is everything regarding the protection and the modification of materials. Yeah, thank you. So these three segments or topics, they are roughly 1/3 of our business, and each and the turnover of the company is roughly 10 billion euros. Next one. And so we are a worldwide company spread all over the world. And again, here our business is divided in three parts: 1/3 in North America, 1/3 in Europe, and the other third in Asia and the rest of the world. There's 21,000 employees at Arkema, and a large part of our revenue are devoted to the R&D with 1,800 researchers. And we have a lot of innovative activities that can be seen with the more than 200 patents that we filed every year. Now, if we are more focusing on materials and on what Arkema is doing on the material on the battery field, so Arkema is a materials provider for batteries in particular, and we are present all along the value chain of the battery. And first from the mining, where we can propose some additives to help the extraction of metals and minerals and metals, up to the final recycling step, with also some chemical products to help for the recycling of materials. And in between, we have all regarding the building of the cell and the pack and etc. So regarding cell chemistry, it's what we are calling inside the cell. I will develop it in the next slide. And then we have everything regarding what we call outside the cell. So it's mainly all the materials that you are using to go from the cell to the pack, so thermal conductor, cell bonding, the electric coating, powder coating, and so on. And also concerning the cooling of the battery system, we can also provide some fluorochemicals for immersion cooling or polyamide cooling system. Thank you. And now, if we look at the materials for inside the cell, so our main product is a PVDF with the brand name Kynar, that is used as binder for the cathode, and also it is also used as a binder for separator coating. It's one of our huge new polymers, polymer other than PVDF. So these are the acrylic polymers that can be used as binder for the anode, for the cathode, or also in separator coating. Another kind of materials are carbon nanotubes with the brand name Graphic Strength. They are used as to improve the connective performance of the cathode, but also of the anode. And then regarding electrolyte, we are providing some advanced lithium salt that are LiFSI and LiTDI. And more recently, last year, we bought a company named Proionic, which are producing some ionic liquids, and they can be used in a liquid electrolyte formulation, but also in gel polymer formulation. You can go to the next slide. Thank you. So what is the role of Arkema in SPINMATE? We have three main roles, I would say. So as a material supplier, of course, we are supplying the PVDF, HFP, LiFSI, and the ionic liquids that are used in the solid electrolyte, so the membrane in between the cathode and the anode, but also in the catholyte, in the cathode. We participate to the development of the solid electrolyte based on PVDF, HFP, and LiFSI. And our main work is to take care of the transfer of the manufacturing process of the solid electrolyte. So from the lab scale, which are several square centimeter, to pilot scale, so several square meter. I think there is you can click. Yeah, okay, so it's, I forgot. Just some clues about the specification of the solid electrolyte. We want to reach a conductivity higher than 1 millisiemens per centimeter room temperature, while keeping performances up to 80 degrees and no flammability under 130 degrees. Electrochemical stability has to be higher than 4.4 volt to be compatible with NMC 811. And the most difficult part is no dendrite formation during the plating stripping experiments in symmetric lithium cells. So now we move to the second part, which is manufacturing at lab scale. So this process was mainly developed by SIC Energy Gune, our partner in SPINMATE, and it ended up with solid electrolytes composed of PVDF, HFP, some plasticizer, some Li salt, and all this composition was impregnating on a porous polypropylene separator. So the process they use at lab scale, so it's in the glove box. First, it's the PVDF HFP solubilization in acetone. Then it is being mixed with the plasticizer and lithium salt. And then it is deposited manually as the solution. No, you can go back, please. This solution is deposited on a porous polypropylene separator with a pipette. So it's a very manual step, as you can see on the picture below. And the last step is the drying. It is dried at room temperature under a small vacuum. And we obtain finally a self-standing film of 80 micron thickness. So now you can move to the next slide. Thank you. So we look at the properties and performances of this film, and they are quite good, as you can see. I will not go into details, but you can see that conductivity at room temperature reach the target because they are higher than 1 millisiemens per centimeter or very close. The oxidation stability is good. It is higher than 4.1 volt upon the different kind of formulation we studied. We have some thermal stability as well, up to 130 degrees. And when we did some tests on lithium stripping plating test, we saw that we can use current density up to 2 milliampere per square centimeter. So roughly, the lab scale solid electrolyte meets the requirement. So next part is now to upscale it. So going from several square centimeter up to many square meters. So it was one of the big work of Arkema, so to produce this solid electrolyte at pilot scale on Arkema's coating line. So you have a picture of our coating line. It is in a dry room in our application center in Lyon, in Sierra Research Center. And just before starting this task, we already knew that we have had some challenge to tackle. So the first one is to automate the impregnation of the porous PP separator, because as you can see, it is done manually. So before upscaling it, we have to know how to do it automatically. Then the solvent used was acetone. It's very highly flammable, so it cannot be used in industry for safety reasons. And it has also a low vapor pressure, which makes it very difficult to be used at industrial scale, because it evaporates very quickly, and the composition of the formulation evolves too quickly to be used for long coating and so on. We also find out that we had some evolution of the lab scale membrane. Properties are good, but we have some plasticizer evaporation. We create the stability over time is not that good. We kind of losing some properties with time. So this is something to be solved if possible with the upscaling. And last but not least, we have to produce a membrane at large scale, but while keeping the good performances of the lab scale membrane, which is always the main objective of the upscaling. So if you can go to next slide. So first we tackle the subject of the automation of the impregnation of the porous polypropylene separator. And we worked a lot on processes to be able to impregnate this porous polypropylene separator. The main difficulty is we have a separator with a low porosity, roughly 50%, but pore size which is quite low. So it's difficult to impregnate it, and we need quite low viscous solution and I would say a low coating speed. So what we ended with was like a double casting. So I put some picture, I hope you will understand. So what we did here is first cast on a PET liner the solution of PVDF, HFP, plasticizer, and LED salt, and just a few seconds later deposit on the top of this first layer, still wet, the porous polypropylene separator, in order to impregnate at least the bottom half of it. And then just less than few minutes later, we cast on the top of this porous PP separator a second layer of the solution to impregnate the top half of it, we can say, with extra solution on both sides of the porous PP separator. So you can see that we finally, because we made some adjustment with the solid content of the solution, with the coating height, with the speed coating, and etc. And we finally got a solution that looks okay. So the bubbles, it's only the PP protective layer. So there's no bubble at the end. That was the main target. So we have something homogeneous, which is transparent because the porosity of the separator is filled with material that has the same refractive index, so it became transparent. And the white part you see on the left is the not impregnated part, which is the white part of the porous PP separator. So it worked, and just one more thing, sorry. And in the same times, we also changed the solvent, and we managed to validate MEK, so methyl ketone, instead of acetone. So MEK has the advantage of having higher vapor pressure, so it is more easier to use it industrially, and it is also less flammable. Oh, so now you can go to next slide. Thank you. So the automation has been made for the impregnation of the porous PP. Now we think on how we can do that on a coating line, because the process is not the same. At lab scale, on the coater at lab scale, you have a fixed liner and the blade is moving during the casting. On the coating line, it's the opposite. You have a fixed blade, because in our case, it's a coating line with a blade. We have a fixed blade and the liner is moving. So the only thing we could think of is to have a roll of cell guard moving and passing through the tank of gel polymer electrolyte and being impregnating that way. The problem is the solution that we are using, as I said earlier, has to be very low viscous, roughly 500 centipoise, to impregnate well the porosity of the porous PP. And this means that it will not only impregnate the PP separator, but it will also spread all over the coating line. So it's not acceptable, and we have to protect it from the low viscous solution. So two options. So what we think about was using a PET liner. We have with two options. First option, a second world with PET liner that will go with cell guard and protect the coating line, or a fixed one if possible, just to protect the coating line from the solution that we are implementing. Unfortunately, after many discussions and studies, it appears that it was not possible, because our coating line, the coating line of Arkema, we can handle only one roll, so only cell guard or PET, but not both in the same times. And ABI we will make because it's like a pilot scale or semi-industrial scale here, and ABI will make the final upscaling at industrial scale, and their coating line was not able to handle two rolls as well. So our equipment was not capable of doing that. And regarding the second option of having a fixed PET liner, it was not possible also, because here you can see a very simplest scheme of the process, but actually we have some intermediate rolls to maintain the film or the collector or the liner you are using, and you cannot put a fixed PET on this. So both solutions were not possible. So the process developed just before is not upscalable on our coating line and on most of the coating lines. So that's why we had to think about a new process and therefore new formulation. So this is the next slide, please. So the goal here was to remove the polypropylene separator, and because it appears that it is too difficult to impregnate at pilot and industrial scale, and to manage because PP separator is I didn't mention it, but it is its game is to be used as a mechanical support to improve mechanical properties of the film. So what we did to counter this removal of PP separator is to increase the PVDF content, and then we also had to change and optimize again the plasticizer and lithium salt to get sufficient conductivity. So this is the work we have done at lab scale too. We have started again at lab scale, and we managed to get a formulation with higher PVDF content and different plasticizer and lithium salt that allowed us to reach good conductivity. So it was not 1 millisiemens, but it was not that bad, something in between 0.6, 0.7 millisiemens, 0.6, 0.7, sorry, millisiemens per centimeter at room temperature. So we validate partially it, conductivity and oxidation stability, and then we move to upscaling. So no, you can. Yes, thank you. So it is theoretically easier because we are now in this upscaling. We have only one step, and we have the same kind of solution that I presented before, but we will cast it on a liner, PET or aluminum, and this is something that is closer to what is usually done on coating line for cathode production, cathode manufacturing, and so on. So we have some experience at Arkema, previous experience at Arkema, and we know that the parameters that you are using for lab scale, usually they don't work for higher scale, and you always have to optimize them. So that's what we done. We firstly optimize the mixing part, which is done with the sync mixer. So we worked a lot on the speed, the time, and also the solid content of the solution. So we end up with a higher batch, and because if you gonna cast several meters, you will need for sure a higher quantity of raw materials. So we end up with a big solution, which was very homogeneous. So we cast it on a aluminum liner, and what we observe is what you see on the left picture is maybe you don't see it very quickly, but just after casting, we have some air bubbles that are forming on the film. The main reason is when we do the manufacturing in the glove box, we let after casting we let the solvent evaporate at room temperature with no airflow or very low airflow. Here in the coating line, it's different. So because after casting you have the furnace, so temperature is close to room temperature, but we have a big airflow to dry that cannot be modified for safety reason, and this high extraction it provoked the rapid evaporation of the solvent and the formation of air bubble. So what we did is to work with on the coating parameters. Also, we changed the saline content. We decrease it because with lower solvent content, you have lower solvent to evaporate at the end. So you can decrease if you are still in the right range for coating, you are decreasing the risk of air bubbles. We work on the coating height as well, and the speed also, and we finally managed to have a film that is very homogeneous with good connectivity. So now we are in the film looks good, and now we are in the process of characterize it to check that we obtain the same performance than the film made at lab scale. So now some takeaways. So I showed you that during SPINMATE project and with the help of SIC Energy Gune, we developed. There was a main leader here. We developed a solid electrolyte membrane with promising performances. So it was at lab scale. Despite all our effort, we were not able to upscale it on our coating line, and it looks like it will be very difficult to do it on general industrial coating lines. That's why we worked again on the formulation at lab scale to develop a new formulation, a new process, and we successfully upscale it at pilot scale. So as I said, Abby will be in charge to do the last upscaling from pilot scale to industrial scale. During this optimization, we saw that the solid content and the nature of solvent are key factors for the membrane manufacturing. So you have to control them very carefully, and the operating windows is quite thin, I would say. And like I said, we finally got an homogeneous membrane that is now under characterization. Just two last takeaways. This example showed that scalability must be considered as soon as possible when developing your new formulation or process. And you have to really think from the beginning on how you will be able to upscale it. Otherwise, I mean, you can have the best materials, the best process at lab scale. If you cannot upscale it, it's like you have nothing. So, I mean, you don't have to put too much barrier because it kills innovation, but that's something to be taken into account for sure. And when the upscaling, if the gap is very high between lab scale and pilot scale, what is also important is to define some intermediate steps to upscale step by step and improve your chance of success. I have some acknowledgements. So first to the Arkema's teams. So both of them actually. So all pilots, all lab scale development were done in my research center in JRL in southwest of France, whereas the pilot scale and the coating line developments were made by the team at CRA, the research center we have in Lyon. I would like also to thank all the SPINMATE consortium, all the partners who worked on this solid electrolyte development, and all the partners of the consortium. And finally, the European Union for the funding of this project. And I have one, yeah, okay. I think there is one last slide, and I thank you, all of you, for your attention.
Yeah, thank you, Hiram. It's an insightful presentation about how to develop and also manufacture the solid polymer electrolyte. Then, yeah, we move to the Q&A session, which is now for all participants. I already opened your camera and mic. Then you can raise your hand if you need to answer something. But now this is the first question, maybe from Rajendra. Can you possible to make solid electrolyte thickness less than 20 micrometers? So yeah, who want to answer for this? Maybe Hiram?
Yeah, I can go. Yeah, sure, you can. With solvent cast, you can do almost any thickness you want. You can go down easily down to 20, 15, or even 10 microns. But then the goal, you have a membrane, but you have also to think about the mechanical properties. And the thinner your membrane is, the lower the mechanical properties will be. So it's a compromise to find in between performances, so conductivity and mechanical properties, and the thickness of your membrane.
So it depends on the skeleton and also the viscosity of the like solution as well. Okay, then we got one. Wait, I got one more here actually. This is for maybe for Mark and Leif together. How you can determine the good, because you mentioned about the how to say, the precursor. So how you can get the suitable precursor to make sure that maybe later your result will be better. I don't know who will answer, Leif or Mark?
Late
answer.
here. So with precursor, you mean the separate salts that are used to make the solution before spray pyrolysis? Have I understood your question?
Yeah, correct.
Correctly?
Yes.
Well, actually, ICP would be a good tool there as well when looking for contaminants, which I guess would be the main possible issue. ICP-MS is probably a better tool than OES, which worked very well to check the composition, but I'm not sure if it's as good when you're looking for something with a much lower concentration as the contaminant would be. But we are mainly relying on the certificate of analysis from our suppliers.
Okay. So yeah, so more or less you can characterize the precursor first, or you can rely on the report document. Okay.
Well,
Yeah.
let me add something on this, because okay, this is the quality of the regions, but it also in the end you will need to do the you will need to synthesize the material and calcine and everything. So you won't be having like the perfect composition maybe from the start. You need to assess first all your process, and then in the end there also do this ICP MS or with spectroscopy. But in the end you will need to assess the final product and then readjust maybe this initial one, because lithium evaporation, it's not always 10%. You can add always 10% exit, but maybe that's too much lithium or too low. So in the end, I believe also you will need to add this characterization by the end of your process and reassess maybe the precursor solution with this information.
Okay.
Yeah, I agree. Also, if you change your setup for calcination, you definitely will have to reevaluate excess lithium. For example, if you move to a more continuous rotary furnace for calcination.
Yeah. And the next part is the ball milling. How far it can affect the crystallinity change for the ball milling? Is there any limit for the parameter in ball milling?
Ball milling, low energy ball milling as we're doing will generally not have a large effect on crystallinity or crystal size. There may be some effect, but it mainly breaks down agglomerates.
Okay.
Yes, just to point out that yes, this one I agree with Leif. You won't be affecting the crystallinity of the samples with low energy. If you go to high energy, then you will likely affect. But it's true that, for instance, in our case ball milling, I think it was good to do it. But if you are using co-precipitation, there's this secondary that are like spherical particles, and if you even with some low energy, you have to look for not breaking those particles.
Yeah.
So if you won't be affecting crystallinity, but you are affecting you could affect the performance of the material with the ball milling in the end. So not much crystallinity, but also some of the performance by the end. So it's something to check that you are not breaking these particles, and
yeah. Okay. Thank you, Mark and Leif. And then another question maybe for Marta. So in this kind of process that you show here, there is a question about before we go to the cell assembly. about the calendaring, is there any particular parameters that you go with the calendaring, or you just put the thickness parameter, or you also adjust the pressure on that?
Yes, so what we monitor is the thickness, and so, well, first the weight and the thickness, and then the pressure of the calendar equipment is monitored. Actually, this is what we fix, and then we make the electrode go through the calendar, and then we measure thickness, and that iterates until we reach to the density and loading values that we want. Sometimes we go over, and then we need to restart. But it's it's the pressure. It's like an hydraulic calendar we use, like in some cases. So yeah.
Okay, and then the next one is like yeah, again, this one maybe Andri already answer about it depends on cell configuration. Again, Rajendra asked about will you use pressure to make a pouch cell? I don't know. This one, the question about after we cell assembly or during testing. Can you enlighten us, Rajendra? Are you here? Which one you want to discuss more?
Yes, the person that is asked.
Yeah.
So I mean, I can answer for both. So to make the pouch, we don't apply a certain pressure. Like what we do, the stack is applied, and then we seal under vacuum the cell, and then we apply pressure. So during the assembly, there's no pressure applied. Is when we mount. So the assembly itself, actually, the ending step is where we have the jig already set on the cell itself. So the cell on itself will not work. So yeah, we control it with the jig in this case.
Okay. So then during making will be no pressure, but for the test, of course, we need the pressure, especially for the solid polymer electrolyte.
I mean, in this configuration, at least. Then there are other configurations, and yes, we hot press like this different process. Like, but and in the SPINMATE context, we don't.
Yeah. Yeah, if you remember I mean in the commercial battery as well, and when we put the pouch cell inside the module, then they will try to limit with the pressure as well, right? Okay,
Yes.
thank you, Marta.
I saw there's another question for me, I think, in the question and answer, not in the...
you can answer. You can answer. Yeah. Oh, I just sent that. Okay.
Yes. So
you can answer if you're...
Yes, the question is, so in the cathode, we didn't use a PVDF system, but PVDF HFP. So if we encounter some issues during the mixing and coating processes. So indeed, we, during the mixing, like one issue we had at the beginning is that our slurry had bubbles. So we don't exactly know if it's from the PVDF HFP, but it can be. So actually, when we have this, what we do is do some degassing. So under vacuum processing or any other methods, we remove the gas of the slurry previous to doing the coating. And then if we control the environment's dew point during the mixing and coating, no, this is not done during the mixing and coating. It's only done during the assembly, because what we do is that we prepare the mixing, we do the coating. Once we have the calendared electrodes, then we dry them, and then we work with them in a dry environment, like in the dry room. But the mixing and coating are not in a controlled dew point atmosphere.
Okay. And I don't know, maybe the next question is, this is for Hirom, I think, given that it's also contain lithium salt. Oh, maybe this is in the cathode side still, or I don't know. Gilang, you want to enlighten in this question, or I already opened the...
Maybe
yes,
I can give...
Yeah. Yeah,
I mean,
you can
in
go ahead.
the recipe for the cathode itself, you write it down. It's also contain lithium salt like LiFSI and ionic liquid because you want to make catholyte as the binder, as far as I know. Is it true?
Yes. Yes. Indeed.
Okay. Do you encounter some problem because LiFSI and the ionic liquid sometimes they have react with another materials, and also you didn't mix in the dry room, something like that. Thank you.
That's, I mean, we didn't encounter problems. It's true that sometimes they react, but that's why it's very important to, like, as when you're doing some cooking recipe in the slurry cooking, it's also very important to keep the times and the steps. So what we do is that we first prepare the catholyte. Very like apart, and we leave it time to stabilize, and then we add the active material, to which sometimes we have some reactive reactions, and then the viscosity of our slurry changes, or the texture. You see it when there's a reaction that occurred. In our case, in these materials, at least, we didn't have so much trouble. But I understand what you mean. Yes, I think it's the recipe in our case. We had some at the beginning problems, but then it worked well.
Okay, thank you, Marta. So I think last question for Jerome is, I think this is also connected with the previous question, that your viscosity, like, I mean, you change the acetone to methylated ketone, and then you change the viscosity as well. So is there any effect for your drying process and also for the end of your product with your change parameter?
Yeah, yeah, exactly. Indeed, I went quite quick on this point. By changing acetone to MEK, there are many differences in the process. For first, solubilization is different because it's harder to solubilize PVDF HFP in MEK than in acetone. So you have to change a bit your parameters, mainly temperature, but also the mixing process, I would say, to be able to solubilize very well, and because it's always a difficult step to solubilize very well your PVDF HFP. And moreover, I mean, because you can always eat, but we are still in a low boiling point solvent, because MEK it's higher than acetone, but it's still below 100 degrees, so you cannot eat too much. So it's a compromise to find between temperature and mixing process. So this is for the preparation first, and then regarding the drying step, the final drying step, actually it's not that different from acetone. It's quite easy to remove all the MEK, and we made some characterization to be sure that we have a very low we have a solvent, very low remaining amounts of solvent, and it's below 100 ppm. So it's at least it's below 100, even more in certain cases. But yeah, you just increase a bit the temperature of your drying step, and you can manage to dry out the MEK.
Okay.
Also,
So only
just
changing.
one maybe.
Yeah.
Sorry, just one comment, maybe the environment. Yeah, so it is important for the cathode, but it's very important for the membrane, because it will be at the end in the pouch side, it will be in contact with lithium metal. So you cannot have water in your membrane. So everything was done at lab scale in the glove box, and at pilot scale in a dry room. 2.55 degrees.
Yeah. So
And even mixing and coating, mixing and coating step was done for the membrane, because here it's very critical, because it's direct contact with lithium metal.
Mhm. So for the temperature, maybe not really a problem, but for the atmosphere, yes, in between the argon glove box and or the dry room, which is quite less than -50 dew point. Then, Mhm. Okay, thank you for everyone. I don't know, is there any further questions for the participants, or we can end our webinar? Okay, I hope this is a positive silence. Then for everyone who need more information or more discussion, you already have the name and the company from every speakers. Then you can try to approach them or approach us in the SPINMATE LinkedIn account or anywhere you can approach. Okay, I think that's all for today. We will try to, if this is interesting for you, then we'll try to see if in the future we'll make some kind of webinar like this. Okay, thank you everyone. Have a good day.
Thank you very much
Thank
for
you.
organizing.
Bye.
Thank you.
Bye.
Bye.
Thank you.
Bye.
Bye.
Bye bye.